phase changes, there are all kinds of things we do. But every experiment otherwise is the same. Okay, so now I've given you some idea how to measure a short pulse. In attoseconds, the details will be very different, but the concepts remain the same. We have to link the frequencies, we have to find a way. I want to end up this part, and then just for the last part of my talk, I want to make the jump towards the basic ideas in the strong field processes. So in order to make a short pulse, somehow we must lock the phases. So we need three things. We need many frequencies, a large bandwidth. We need a spectral bandwidth that's big. We need each phase or each frequency locked to the others, kept in phase with the others. And we must not only get them in phase, but as they propagate around in the cavity, we must keep them in phase. This is a modern femtosecond laser, which can go down to about a cycle or a few cycles if it's carefully designed. And it has very few elements in it. It has mirrors that are always essential for the laser. It has a gain medium. Ti sapphire is frequently used because of its very large bandwidth, satisfying the many frequency criteria. It has a nonlinear element, although it's not obvious. The nonlinear element is actually Ti sapphire itself. I'll explain to you in a minute. And it has a set of prisms along the pathway, and those prisms are there for dispersion compensation. And so I'll describe that to you as well. And these are the two critical elements in a modern laser. A nonlinear element, which is the material itself in many cases, and some method for phase or dispersion control, which in this case is two prisms. So let's deal with the issue of dispersion control first. We've already discussed this a little bit. If we have a very short pulse by hypothesis, and we bring it into a material, just low intensity, ordinary propagation through any material, every material has a refractive index as a function of frequency, except the vacuum. And so every material will disperse the pulse. The pulse that comes in, that could be transform limited, comes out with a chirp in it. You recognize that. We described it before, a chirp pulse. And in fact, the chirp pulse will look very much like this, with the red in the front and the blue in the back. For most materials, this is normal dispersion. So when you make an oscillator with two mirrors and you think of the frequencies that can sit there that will add together to give you the short pulse, a real oscillator has frequency-dependent mode spacing because the dispersion of the material makes the material effectively a different length for each frequency. It's exactly like a real molecule versus a harmonic oscillator. In a harmonic oscillator, the levels are separated by an equal spacing, each level one from another. In a real molecule, you have a non-harmonic potential, and the vibrational modes are separated by something that are not equally spaced. If you create a wave packet in the molecule, it only moves a couple of times until it disperses, and it's almost unrecognizable after a few oscillations. If you create a wave packet in an oscillator, a short pulse, if you don't do something, it will also spread out in phase and become unrecognizable over time. So in order to overcome this, we need some sort of dispersion compensation. So it turns out that the refractive index has two effects, of course. The refractive index, as we all know, creates light that separates in a prism. That's effectively the dispersion of the material, that the refractive index is different for each color. And of course it has the effect of giving us a chirp pulse as well. One in time and one in space. And so, although it took 20 years in order to discover this from the beginning of mode locking, and people worried about how to get around the problems of pulse dispersion, it turns out it's quite straightforward. You try to get dispersion in space to compensate for dispersion in time. Let me just show you how this works. Let's assume we have a short chirped pulse coming into the material. The different colors, when they come into a prism, are dispersed differently. The light goes through a different path, depending on its color. And when it comes up to a second prism, correspondingly positioned, as shown here, the light will compensate and go back parallel to itself. But you will find, if you come out here to a wavefront, and you trace the path length in space, and the path length through the material, the effective path length, you will find that the different colors have gone through different path length. And so you can have one color catch up to the other. In fact, it works very well, so you get normal dispersion, and by putting in a prism compensate pair, you can compensate for normal dispersion. The blue will catch up to the red. However, they're offset, as shown here. The blue now is offset to one side, the red to the other side. If you put a mirror and bounce it back on itself, it undoes itself in space, but the path lengths remain equally or doubly different. And so you can have now the blue catch up to the red without the spatial consequences that seem so devastating when you think of a prism in the first place. All beams, all colors are still going parallel. They're going parallel in the opposite direction. And depending now on how much material you put in, move this back and forth, this has normal dispersion and this has anomalous dispersion. You can compensate and make them balance, so normal and anomalous dispersion equal each other. And that's what's done in many modern femtosecond lasers. And that's the reason for the prisms. Now the second thing I want to talk about is how are the phases locked? How are the phases locked together? This is done by Kerr lens mode locking, the Chi-3, the process, the nonlinear process I talked about in the first place. All frequencies approximately the same thing. But it's easy to see this qualitatively if you think about it. Imagine you have a low intensity pulse coming into a piece of material. Any piece of material is fine. In practice, it will be the Ti-sapphire crystal that will be the lasing material that is the nonlinear material as well. If it's low intensity light and the sides are parallel, it's just a block of glass or block of material, nothing happens to it. However, if it's high intensity light, the refractive index depends on the intensity in this form, n sub 0 and n2 I, where I is the intensity. And the intensity has a spatial property to it. The intensity is a Gaussian beam or something like a Gaussian beam in all cases. It doesn't go on forever. And so the light that propagates in this case will have its phase delayed because of this extra refractive index relative to what's out at the edges where the intensities are low. And so the beam will naturally be focused as it propagates through. This is like self-focusing. It's really the same idea as in self-focus. In fact, its frequency content will also be increased. But it's sufficient here to think of only the spatial properties of it. So a real pulse, which has low intensity at the front, high intensity in the middle, and low intensity back here, goes through unaffected, unaffected, focused. Right? So that's what happens, and that happens inside the laser. Here's an illustration of that process. Here's the pulse coming in. It comes into the nonlinear crystal here, through a lens or through mirrors, but through a nonlinear crystals. The part that's best focused comes out, and you just set up the second lens, so that's the one that couples back into the cavity best. And all of the low intensity stuff doesn't couple nearly so well into the cavity. Now you favor, the cavity favors the high intensity part, or the part right in the center, and it suppresses the stuff out in the edges, the low intensity pulse. Squeezing on the pulse. Every round trip in this cavity, the pulse is squeezed shorter and shorter and shorter until it can be squeezed no more. And so that's what it looks like. That's a relatively modern femtosecond laser. It has almost no components, mirrors. These are just mirrors to concentrate on the nonlinear crystal, so just a set of 4 mirrors. Tie-sapphire material for glazing. The beam set up optimally for self-phase modulation here, linking all frequencies in the cavity by this squeezing that I described to you before. And then its dispersion is controlled by a prism sequence. In some lasers, you will see the prism sequence removed, and you can put chirped mirrors in all places where you have mirrors to replace the prisms. Those are sometimes better because there's nothing to move, but sometimes they're worse because there's nothing to move. So it depends on your perspective. If you don't want to touch anything, get chirp mirrors. If you want to be able to optimize, then play with prisms. So there's the pulse I showed you before, and that's made by a system just like this. Okay, so now I've covered, I hope, how you describe short pulses, the technology for measurement, and the technology for making them. I won't talk about amplification, that's also important, but this would be only lasers then. I want to use the last, I have about 10 minutes left, my last 10 minutes to make the jump towards the physics of Attosecond. So the next thing is the other kind of nonlinear optics, extreme nonlinear optics. That's what allowed this jump in pulse duration, this changing in the slope, and allows the advances that have taken us to Attosecond. To me, in some ways, this all starts out 50 years ago. 50 years ago, Keldysh, writing in the Soviet literature in 1964, so it was 1964, wrote a paper which he called the ionization in the field of a strong electromagnetic wave. In this paper, he described placing an atom or a solid. He did both. They were simultaneously treated inside. In the case of a solid, you can think about a band-to-band transition. In the case of an atom, you think of ionization. So ionization is what was termed by the deals with solids as well. And in this paper, he said, if I were to think about using infrared, strong electromagnetic infrared pulses, long wavelength, well, he actually does with many pulses, with many frequencies, but infrared is the most interesting here. If I think about interacting with infrared pulses, if I satisfy the criteria shown here, gamma squared, where this is now called the Keldysh parameter for him, where gamma squared is given by IP, IP being the ionization potential, or the band gap, whichever you wish, over 2UP, where UP is the energy of an electron oscillating in an electromagnetic wave, just a free electron, otherwise at rest, just oscillating back and forth. And this is the average energy of this, called the ponderomotive energy. So over 2UP, if this is satisfied, then you can think about the removal of the electron from the atom as tunneling. So this is an amazing idea. It's obviously not tunneling. Tunneling is a DC effect. You place an atom in a field, and everybody studied it in the 1930s. People discovered that you could tunnel electrons from atoms below their barrier, and the electron just appears in the continuum. So he said exactly the same mathematics applies. You can think about this almost as if the field were static, even though the laser field can be quite high frequency and still satisfy this condition. To give you some idea, UP is the classical motion of electron. It's about 6 eV for 800 nanometer light and an intensity of 10 to the 14 watts per square centimeter. You can scale everything else from there because there's the formula. And if you want to think about it solid, if you want to think UP is 2.3 EVs for 3 micron light and for 2 times 10 to the 12 watts per square centimeter, and I almost certainly thought of that as a free electron mass that is a fraction of the free electron real mass. I think maybe I'm not. I have to work that out and check. You might want to check it. In solids, the electron or the effective mass is much lower. And I may or may not have put this in. This has been a highly influential paper. To me, it's really important because it's just amazing. He made this statement that an electron tunneling out of the system and into the continuum is this beautiful process. It looks like a beam splitter, if you will. It's amazing that a static field theory describes something that happens in the time scale of the laser pulse changing the field, and the window open for tunneling inside, say, an 800 nanometer laser pulse can easily be only around a few hundred attoseconds. So amazing again that a static field could, a static theory could describe this. So, thus in 1964 made the first step towards attosecond science, I think. And even inside his paper is the second step. He never commented on it. I don't know how much he thought about it. And the second step was to say, what happens to the electron after it's created? I won't go through these equations. They're relatively straightforward. They're just equal F equals ma. If you think about the field, the laser field, E as cosine omega t field, and we think about the electron as tunneling out, being created by tunneling out, let's imagine it tunnels out at some time, and we can associate the time. Then we can solve F equals ma, and we can calculate the characteristics of the electron born at any given time as a result. And this is such a calculation. And you find out the velocity of the electron as a function of time is equal to an oscillating term, electron oscillating in the field, plus a term that depends on its time of ionization, its time of birth. That's T prime in here. This is the beginnings of the ideas of a trajectory. An electron comes out. If the electron comes out, you can follow what it did. It was born at time T prime, all its characteristics by classical physics. So I just told you how to do that. I didn't go through the calculation because I don't think you need to see F equals ma, nor do I have the time to do it. But just to make it clear, the electron is born somewhere. There it is. V equals 0, T equals some time. Calculate from then on for all different phases of birth what is the characteristic. And you'll find out an awful lot about what we will see in attosecond science. Actually, if you do that, do the same thing for circularly polarized light. An atom, Coulomb potential in a field. The electron is born at some time, the field pointing in some direction. Calculate what happens to that electron in circularly polarized light. Change the phase, look at all possible phases. You'll see it's extremely different, linear versus circular. Very different behavior, very different results of the calculation. And when you're done, you will understand a lot about trajectories, and you will understand the essence of the Atto clock that many people talk about. So anybody wants to know about the Atto clock, I wasn't going to talk about it, and I doubt anybody else here will. Come and find me, and well, work this out. This is all kind of interesting to do. It's freshman physics. It won't take you very long, and it'll give you a feeling in your fingers for an awful lot of attosecond science. Okay, so what Kaldis didn't understand, what he didn't recognize, is the next step. So here is this classical-like view of an atom. I told you that a moment of birth maps by F equals ma to a trajectory of the electron. You can calculate what time or under what circumstances that the electron might be driven back and collide with the ion from which it went. Let me just make it clear that it could easily happen. The field is pointing, say, that direction, or force on the electron is that direction, I don't have to worry about the charge. The electron is pulled away, the field changes its direction, the electron is driven back, collides, recombines. Okay? It turns out that for fields more or less anytime after the peak of the field and for the next quarter of the cycle will be driven away and has a chance to come back and collide. And when it comes back and collides, it can recombine. It turns out that for an electron born late in the field, it will come back earlier with low energy, recombining, giving out its energy as a low frequency photon. If it's born a little earlier, it comes back, giving out more energy as a higher frequency photon. And finally, there's an optimum time of birth in which it comes back and gives out the highest frequency photon in the problem. And that gives you this is the essence of the attosecond pulse. Okay, so first thing you see a large bandwidth given by F equals ma. You see a chirp on the pulse, just like we described before. It's a red chirp, or it's a blue chirp, right? It's going from red to blue. You'll see if you do F equals ma that the frequency of the electron coming back depends on the wavelength of the light that's driving this, the ionization potential of the atom, and then we need the tunneling. Depends on the field at which the electron is born and things like that. But this can easily go up to a kilovolt. Not easily, but it can go to a kilovolt under some circumstances. And so the bandwidth can be huge, and it's frequency coded or chirped pulse, just like we described before. Okay, so just to make sure that, yes, please.
How do I see that with many atoms, this process will give you a coherent light?
Yeah. So I was going to do that. Can I wait just 2 or 3 slides? I'll just comment it. But I'll spend some time on it as much as you wish. But if you don't mind, 2 or 3 slides later. I know you all study quantum mechanics, so I can't just leave classical physics in the nano. And I'm almost done. I know I'm almost done. So I want to make sure right away that you make the transition from classical physics and from classical trajectories to quantum trajectories. So here is a quantum mechanical illustration, like a quantum mechanical picture, if you wish, of how that process works. You have an electron, bound electron, now a wave function. The electron splits, creating an electron left in the ground state, plus an electron wave packet in the continuum. That tunneling is fine. Cavity's dealt with tunneling. That's a quantum mechanical effect intrinsically. The electron, of course, is phase related because it tunnels from the ground state out to the continuum. The wave packet propagates. That I really need a movie to show, so I'll have to illustrate it. And some portions of that wave packet, the wave packet gets pulled apart and changed. And some portions of that wave packet are driven back to overlap the wave function from which it left, creating finally an interference or a dipole in the atom as this interference coming back. So a quantum perspective is a bit like an interferometer, an electron being driven out, driven back again. Classical physics gives you the trajectories. You can make it semi-classical physics and get the electron phase along the trajectories. And the sum of all trajectories, all moments of birth, give you the wave packet that I've described to you in quantum mechanical language. So this is a wave packet, which is a bit like a sheared interferometer.
So which fraction of the electron gets handled typically?
Excuse me?
Which fraction of the electron gets handled in typical experiments?
Generally, we don't tunnel, you need something back here, right? There's no,
Right.
It's clear, you need something back here. You can't go back to an empty state.
Right.
This is like any nonlinear process. You go back to the state from which you left, and you left lots of population. 10%, 5%, something like that, small portions. Depends on the experiment. But you don't generally do too much. Okay, so I just wanted to do the last thing. I just want to give you a qualitative picture for this interference or this final step. And so you understand the whole ideas of the coherence. So this is taking and isolating that overlap. Let me just make sure you understand what I'm talking about. Here is the overlap between the wave function and the wave packet. I'm only going to concentrate on that part. The wave packet is going to go across this thing, and it's going to do its, and it's going to, I'm just going to take a moment in that interference. There it is. And now I've got it coming back again, and you can see the superposition. I just want two wave functions in this case. A Gaussian plus a reclusion plane wave. And there's the sum of the two here, and there's the the sum of the two, and well, that's the sum of the two. This is the square to give you the probability, and that's the dipole, therefore induced. And as the wave packet moves, in this case going in this direction, the interference changes. The square is there, the dipole is there, and so you can see the dipole oscillation. The dipole first was there, now it's here. As the interference evolves, it moves back and forth. An oscillating dipole emits radiation. The radiation that's emitted is the radiation that you see. This is the attosecond or high harmonic pulse, the XUV radiation. That's interesting. This is the dipole, the strength of the dipole that's induced in a plane wave approximation. And the dipole that's induced is the transition moment, or essentially the transition moment. So the electron recombines or induces a dipole two ways to see it. So you can see that the radiation that's created, that's going to become this attosecond pulse, the radiation that's created has an amplitude and phase given by the amplitude and phase of the recollision electron as translated through the transition moment of the atom as it goes back down to the ground state. Okay. I want to make, as I end up this part, and I'm going to almost end and only do a couple more, and I'm coming back to your point, I think, the next one. A couple of things just to make this now practical. The pulse I showed you in the first was only one cycle. You can't make a one-cycle pulse that stops anywhere like I did. You need some real pulse. Mostly in many laboratories we have a multi-cycle pulse. This is not realistic either, but you can imagine the pulse. What happens in that case? The wave function, a piece of it ionizes, creating a wave packet, comes back, recombines, giving you an attosecond pulse. This happens the next time and the next time because the wave function can be multiply divided. So we create a train of attosecond pulses, one, followed by another, followed by another, followed by another, each separated by half a period of the laser light, a frequency, a set of pulses, one after the other, separated by half a period is a set of frequencies. And so if you look at that in the spectrograph, this is a set of frequencies. These are called the high harmonics of the laser light, and the harmonic number can go in many experiments from 1 eV approximately to 100 eV, so 100 harmonics. And in experiments done in the infrared, you'll probably hear about from Margaret Renee tomorrow, you can go down up to 3,000, I think it is 3,000 harmonics. Infrared driver going to kilowatt. So this is the process of high harmonic generation. Attosecond pulses, almost the same thing. Okay, so now I come back to what I'm going to say. So of course, I've talked about one atom. And I've talked about a laser beam coming in, so let's make it realistic. Here's a real setup. The laser's out here. All complexity is in the laser. If you want to make an attosecond pulse, you've got to do something to the laser. The beam is focused into a jet of atoms, or a cell of atoms, or a fiber of atoms, or molecules, or in fact even solids it can be in some circumstances. The jets that we use are supersonic jets because we do a lot of work with molecules, supersonic jets. The beam is expanded into the vacuum. It's approximately 10 to the 18, maybe 10 to the 19 atoms per square centimeter, cubic centimeter. The length of the jets are in the order of a fraction of a millimeter. So that's the number of atoms that we're dealing with. But other people, you'll hear here, use cells, which can be longer. They can be fibers. It's basically a cell or fiber. It's like a cell. So there are different ways you can do this. These are not just a single atom process. So now, why does every atom work? As you go along, the laser beam sees one atom randomly positioned. It ionizes, electron comes back, makes a wave packet, and now the wave packet and the light propagate along exactly together. They find another atom. The next atom ionizes, electron comes back, recollides, creating a wave packet which is identical to the first, as long as the first propagated with C, phase matching again, propagated with C along with the fundamental. Nothing about the atom remains. We took the electron from a wave packet, from the wave function, and we returned the electron back to the same state from which it came. Nothing with the atom remains. Only the light comes out. We don't know if it stayed there. We don't know if it went